Like half the lesson.
So there used to be.
So violent over there.
Wow, that was snappy.
You gotta keep the little ones in mind, you know?
Is this, did y'all plan this to kind of have
You
the
want
same
one?
color of
No.
like cans or water?
Yeah, we match them every day.
It's kind of weird. Okay. All right. So we used to have, and they fixed it. So over, especially the North and South Pole, primarily over the South Pole, they would develop what they call a hole in the ozone. Okay? And this was important because of the fact that, so ozone looks like oxygen, but instead of being a diatomic molecule, it's what we call triatomic. Okay? So there's 3 oxygens hooked together. So this is important because ozone has a unique capacity to block UV light. So what they were finding, and it was cyclical, it wasn't all there all year round, but you would get literally, if you just Google hole in the ozone, okay? And so they were finding that this ozone was being depleted, which is bad, because then you don't have the ozone to block the UV light. Skin cancers will then go up. UV light is, because UV light, remember, has much more energy than normal sunlight does. Okay? So this is bad. So they figured, hey, what's causing this? Turns out that it was aerosols that we were using, especially in refrigerants. They were hastening the breakdown of the ozone. We stopped using that particular type of freon in refrigerants. Hey, the ozone hole healed itself. Okay, so that was one of the big wins for chemistry. Nathan,
what's the gas we put in our AC?
it varies. It might be like, I want to say like R140 or something like that, because they reformulated it because what they used to use was freon. That's what they used to use, but now because the freon was what was causing the hole in the ozone.
Don't you still use it in your car?
No, but unless it's a really old car, they use a version of it, but they can't use pure freon anymore.
I think they can still call it that.
Yeah, but it's not. It's not pure. It's not the original form of freon. Okay, so notice that you've got these double arrows, which means this reaction can go forward and backward depending on the situation. It's still balanced. I still have 6 oxygens on both sides. Okay. Laws of chemistry still hold. We still have to balance the reaction. So this might be something simple, relatively simple. So we know that we're producing oxygen at the rate of 6.0 times 10 to the 5th molarity per second. Okay, so this is a rate function. So meters per second is molarity per second. So we're making oxygen. Okay, so if you go with the sandwich analogy, instead of making sandwiches, we're making oxygen. So what I want to figure out is what's the rate that the ozone is being consumed to make the oxygen. Now, if you want to go with the formulary thing, okay, so the ozone, that would be -1/2 times the change in the concentration of O3 per unit of time is going to equal 1/3 times the change in concentration of the oxygen per unit of time. Okay? So what I gave you was this number. Okay? So we know the rate at which the oxygen is being produced. What we don't know is this number, the rate at which the ozone is being consumed. So at this point, it kind of turns into an algebra problem. Now, for now, don't worry about the negative sign. We'll put the negative sign on the end because we're talking about the rate at which that's being consumed. So when you do the math, don't get hung up on the negative sign. The negative sign just indicates that, hey, this concentration is going down. That's all it's telling you. So if you want to look at this, so we know this number, I want to get this by itself. So what am I going to do? Yeah, so I need to get this by itself, so I've got a 1/2 in front of that, so I'm going to multiply both sides by, or by 2, because I want to get rid of that. So my change in my concentration of O3 per unit of time is going to equal 2/3 the change in concentration of my O2, which is 6.0 times 10 to the negative 5th molarity per unit of time. And if you do the math, you get negative 4.0 times 10 to the negative 5th molarity per second. Okay? So, and the negative sign just floats in there because of the fact that we're talking about something being used up. That's where that comes from. Now, again, if you don't like this, like for Chem, I'm a stoic kind of person. Great. So if you wanted to, you could sit here and go, okay, well that's 6.0 times 10 to the negative 5th, and that's your oxygen per unit of time, okay, per second. And then you can just look at this in terms of stoic, and you can go, oh, okay, right. In front of the oxygen, there's 3 moles of oxygen, and then there is 2 moles of O3 being from that mole ratio. Notice that in both situations, you multiply by 2/3. Okay? It's how you want to think about it. You can do stoic, you can, I don't care. Now, but if you were specifically asked to write the reaction in terms of, or an expression for the rate at which the O3 is consumed, then you would have to do something like that if you were actually asked to write the expression. But if you just want to find the number, you can do either one. I don't care. Do the stoic. Doesn't make any difference. Okay. Got that. We're good. Okay. So I don't know why your book does this. It takes this whole unit and breaks it up into 2 chapters. So this is going to be weird because this assignment is going to come from 2 different chapters. Don't flip out. Some of these are even like simple true false questions. So, all right. I gotta find it. Hold on. I got the numbers that I've got right now. Okay.